So we'll start with a logical puzzle in this session. Okay. So let's say there exists some island in our make-believe world that where we have only two kinds of inhabitants. Okay. One kind are knights who always tell the truth. Always. They cannot lie. They always tell the truth. And the other kinds are knaves who always lie. They're incapable of telling the truth. The knaves always lie. Okay. Now you go to the to the island. Let's say you go to the island and you encounter two of the inhabitants from that island. By looking at them, you cannot tell whether they're a knight or a knave, right? So there's no way to tell by looking at them. All we know is the knights always tell the truth and the knaves always lie. That's all we know. Next, what we know is, let's say the two inhabitants that you encounter, let's say that their names are A and B. Let's say A tells you that B is a knight. A makes the statement that B is a knight. And B makes the statement, B tells you that the two of us are of opposite types. Okay? So, based on this, you would have to find out what is the identity of A and what is the identity of B. Okay? So, how do we do this? So, before anything else, let me tell you that in these puzzles or in propositional logic, in the entire idea or entire topic of propositional logic, the more important thing than the result or the final answer is the logic, how you build it up. All right. In this class, if anybody comes up with any answer, I will take that to be correct or true as long as you can back it up with your logic, as long as the logic that you have built behind your conclusion holds or makes sense. Okay? So the logic is more important. Now we will go by the logic step by step. Some of the other things that I want to remind you, that when you come into this class, assume that you're explaining things to a computer which does not know of the outside world. The computer does not know anything. It has no memory or no understanding of anything. You are training the computer to understand or to be able to make logical deductions. So the computer does not know of our world. The computer has no common sense. So the common sense that you have derived based on your experiences so far in your life, leave that outside of this classroom. We only go by what we know given in the scenario. In the scenario, we know that knights always tell the truth. In the scenario, we know that knaves always tell a lie. And in the scenario, we know that the inhabitant A makes the statement that B is a knight, and the inhabitant B makes the statement the two of us are of opposite types. Based on this only knowing this, we can start our logical deduction. Now, the way to do these things is first go by an assumption, whichever one. Let's say we go by the assumption that A is a knight. Let's start with this assumption. Now, if A is a knight, in that case, what do we know about knights, guys?
They always
They
tell
always
truth.
tell the truth.
That means the statement that A made, the proposition given by A, must have the truth value of true. The statement made by A must be true. That is, B is a knight. This statement must be true. If this statement is true, then what does that tell us about B?
It's false.
We always tell the truth.
We'll get to whether it's false or not later on. Remember, again, more important is how you build the logic before you get to the conclusion. All right. So, where were we? A was a knight. That was our assumption. And based on that assumption, the statement B is a knight made by A is true. That tells us that B is a knight too. Now, if B is a knight, then what B is saying must be true as well. What is B saying? B is saying that the two of us are of opposite types. Wait now. If the two of us are of opposite types, two of us are,
Contradicts.
if this is true, if this statement is true, so far we have seen, so far based on our assumption, we have seen that B is a knight. Now if B is a knight, what B is saying is true. However, this leads us to a contradiction, because if what B is saying, if that is true, then the two of them are of opposite types. But so far we see that both of them are knights. They are not of opposite types. So there is a contradiction. If both of them are knights, as we have seen so far based on the assumption, if both of them are knights, then this statement is true. However, if this statement is true, then the two of them have to be of opposite types, which is not the case. So a clear contradiction. So one of you said that it's false, you're correct, and I'm sure that what I'm saying, all that I'm saying, you already had that in your head as well. All of you who came to the conclusion that our assumption, the assumption that we started with, the assumption that A is a knight, and which led us to the conclusion that B is also a knight, cannot be true because it leads to a contradiction. I'm sure that most of you had that in your head. However, it's important to lay out your logic when you're explaining these things step by step. Every small step has to be mentioned. You cannot miss any step. Okay? Think, like I mentioned, think of this as training a computer which does not know anything. So you have to tell it about every single step. All right? Every single step. You can't just assume for the computer to understand or work out the steps in the middle. Okay, so our assumption that A is a knight must not be true, because it leads us to the conclusion that both of them are knights, and if both of them are knight, then we have a clear contradiction based on what B said. Okay. So there is a contradiction between these two statements then. Now our hypothesis, our assumption must be false. In that case, we have to go with the opposite assumption then. What is the opposite assumption? That A is a knave. Now we go by, what if A is a knave then? If A is a knave, if we assume that A is a knave, then what A is saying is a lie. That is, A's statement is false. That is, the opposite of A's statement is true. What is the statement A made? B is a knight. This statement must be false because A will lie, since A is a knave. If this statement is false, the opposite must be true. What is the opposite of this statement?
B is a knave.
B is a knave.
The opposite of this propositional statement is B is a knave. Now, if B is a knave, then what B is saying is also a lie. Then this statement, the two of us are of opposite types, this statement no longer has to be true. We know that this statement is false. We know that this statement is false because so far, based on the assumption that A is a knave, so far we come to the conclusion that B is also a knave. So what B is saying is false, right? So if what B is saying, if that is false, in that case, the two of them are not of opposite types. If what B is saying is false, then what statement is true? Which one will be true? The opposite of this statement. What is the opposite of this statement? That is, the two of us are of the same types. Yes, exactly. Exactly. So, if the two of them are of the same types, and if both of them are knaves, everything checks out, right? Everything falls into place. Everything makes sense. So, we see that the hypothesis that A and B are knights, or A is a knight, which leads us to that, leads to a contradiction. And the hypothesis that A is a knave makes sense. Everything checks out. So it must be true that both of them are knaves. So finally, when you have to determine the identities based on these two deductions, these two parts, you can say that A and B, both of them are knaves. Okay? So what if instead of, so here we started with the hypothesis that that A is a knight. We started with that. We started with the hypothesis that A is a knight, and we saw that from that, it led to a contradiction. If it leads to a contradiction, the hypothesis must be false. So we went with the opposite hypothesis and saw that everything checks out, everything falls into place. So that must be true. So A and B are both knaves. What if you started with this hypothesis? What if instead of starting with, okay, A is a knight, instead of starting with that, what if you started with the assumption that A is a knave? What if you started there? what would happen in that case? In that case, based on that assumption, you would see that everything checks out, everything falls into place. So you could say that, okay, my assumption is correct. However, that is not enough. I would recommend, even if your assumption leads to a conclusion which agrees with everything, where it makes sense, where there are no contradictions, even if you have that, don't straight away go and say that, okay, my hypothesis is correct, my assumption is correct, so both are names or whatever. Even if you see that everything checks out based on your first hypothesis, show that the opposite hypothesis leads to a contradiction. If you see that everything checks out, by now you know that, okay, my hypothesis must be correct. Still, you should show, even for yourself, you should see that, okay, the opposite hypothesis actually leads to a contradiction, so we can say for sure that the original hypothesis was true. Does everybody understand what I'm saying?
Yes.
Yes, ma'am.
Okay, all right. So yeah. So for example, here I started with a hypothesis which led to a contradiction. That's why I went to the other one. If you started with a hypothesis which made sense, for example, in this case, if you started with A is a knave, instead of starting with A is a knight, if you started with A is a knave, that assumption, then you would see that everything makes sense, right? Do you stop there and say that A and B both are knaves? No. Usually, I would recommend that usually try to go to the other hypothesis, the opposite hypothesis, and show for sure, to be sure completely, show that the other hypothesis, see, this leads to a contradiction, so my original hypothesis must be true, so both of them are knaves. So that's how you do it. Okay. All right. So any questions regarding the answer that we got to?
So means these puzzles can have can't even have contradictions. There's a chance that they won't have like contradictions if you approach from two angles.
No. These puzzles, you will see that the answer, you will have only one path where there are no contradictions. However, if we ever set a harder puzzle for you, where you see that there are multiple paths where you can where there are no contradictions, you can just go ahead and state all of them, or you can state one of them, or explain your entire scenario. Again, like I've mentioned right at the start, in propositional logic and related both A and B are both names and knights. It's not possible at all. As you can see, based on the definition, it's not possible. However, what if there was a puzzle where you could have two answers? That's still fine. Remember what I said. What's the more important thing? How you back up yourself with logic. How you lay down your logic, including every single step of your deduction. That is the more important part, the work behind, all right? So whatever the scenario, whatever your answer is, back it up with logic and you're good to go. Now, how do we lay down the logic when we write it down? We've discussed this whole thing using natural language. How do we do it? Using propositional variables. Because in these puzzles, you can represent each and every statement using a proposition. And that is what you are actually expected to do. For example, the statement that A is a knight, B is a knight. These statements, that is, these assumptions can be, these are propositions. A is a knight is a proposition. It can either be true or false. B is a knight is also a proposition. It can either be true or false. These propositions can be represented by variables. Here we are representing them with P and Q respectively. All right. And ultimately, the answer comes down to the truth value of P and Q. All right. Whether P is true or false and whether Q is true or false. Ultimately, the answer comes down to this, right? So P and Q represents the propositions. A is a knight and B is a knight, respectively. And the statement not P and not Q will be the opposite of the propositions. That is, not Q will be A is a knave and not Q will be B is a knave. All right. And from there, how did we lay down the logic? Just look at that. So first of all, our first assumption, what was that? A is a knight. If A is a knight, we are going with P is true. We are assuming that the truth value of the statement P is true. We are assuming that P's truth value is true. Okay. In that case, as we saw, if P is true, then what A is saying is true. What is A saying? A is saying that B is a knight. That is, A is just giving you the propositional statement represented by Q. If what A is saying is true, if P is true, then what A is saying is true. And in that case, Q becomes true as well. That is, if P is true, then we have Q is true. If P is true, then Q must be true. Okay. Based on what A said, based on the statement A made by A, if P is true, then Q is true. However, what is the statement that B is making? Because if Q is true, then B is a knight. And if B is a knight, then what B is saying is truth, is the truth as well. Now, what is B saying? B is saying that the two of us are of opposite types. Now you have a proposition or a statement which is a bit more complex. Okay, so you will have to represent it as a combination of the variables P, Q. Okay, the two of us are of opposite types. If the two of them are of opposite types, what does that mean? It means that if A is a knight, that is, if P is true, then B must be a knave. That is, not Q must be true. And if A is a knave, that is, if not P is true, then B must be a knight. That is, Q must be true. Or in other words, we can represent it in this manner. What did B say? That we are of opposite types, right? So we can represent it in this manner. Either this is true, that is P and not Q. P and not Q is opposite, right? What is P? P is A is a knight. What is not Q? Not Q is B is a knave. So opposite types. So P and not Q. Both of them combined with and, because they have to be of the opposite kinds. Or in other words, if it's not P, what does it mean? A is a knave. Then B must be a knight. So not P and Q. All right. So we represent it in this manner. Either this is true or this is true, based on the statement that B made. Is everybody with me so far? How we can represent B's statement? The two of us are opposites type. This proposition can be represented using variables in this manner. Is everybody with me so far?
Yes, ma'am.
Yes,
Okay.
miss.
Yes, miss.
Okay. Now, think about it. This is the statement that B made. This statement that we have here. And so far we established that B is a knight. So this statement must be true. However, we've also established that A and B, both of them are knights. In that case, P is true and Q is true. Both of them are true. If both of them must be true, then what do we have? We have the statement P and Q must be true. But is P and Q here in any of these parts? See, is P and
No,
Q
no,
here
no.
in the first part? No.
No.
Do we have P and Q in the second part? No.
No.
Now think about it. If P and Q are true, if P and Q is true, in that case, if P and Q is true, in that case, what does it mean? Both P and Q are true. That is what we have seen, right? P is true and Q is true. If both P and Q are true, then what happens to this part, guys? If both P and Q are true, we have an AND operator here as well in the first part here. If both P and Q are true, what happens here? What happens to not Q?
False.
Exactly, this becomes false. Because if both P and Q are true, then not Q becomes false, and that makes this statement false. If both P and Q are true, here not P becomes false, and that makes this statement false. So you have false or false. So there you have P and Q is true, and here you have false. So you see the contradiction when we represent it with propositional variables as well. Excuse me. So you see, you can represent the contradiction that we discussed a while back, just using our natural language. You can represent the contradiction using propositional variables and logical operators in this manner. So if this statement is true, then our statement P and Q cannot be true, the previous conclusion that we came to so far. And if that one is true, then this one cannot be true. So we have a clear contradiction. So A and B cannot be knights. Our assumption that A is a knight is false. So the opposite must be true. What is the opposite? The opposite is not P. Not P. What is not P? A is a knave. And then you do the same thing that you've seen here. You do the same thing for the assumption that A is a knave. That is, not P is true. For not P true is true, you do the same thing, and you will see that for that case, even using propositional variables for that specific scenario, you get to a conclusion where there are no contradictions using propositional variables. And that is how you lay down your logic using propositional statements and variables. All right. Can anybody tell me that this statement, the two of us are of opposite types, this statement that B made, this statement, this proposition, can anybody tell me about a different representation of this proposition? Different, by different I mean using a different operator, something that you've already studied actually.
Yes, miss. Or and. Like first we have to combine with
Exclusive.
or.
Come again?
Can we do exclusive?
Yes, that is the answer. Exclusive or. The all right, so the XOR. Was there an issue with? Okay.
Yes, miss. There was an issue with the audio.
Okay. All right. Oh, sorry about that. I think there are some problems here on my end with the Wi-Fi. All right. Please stop me at any point if you see that you cannot listen to me, or there is lag, or there is some robotic noise or whatever at the background. Please stop me at that point. I'll just switch to mobile data then. All right. Okay. All right, so that's how you lay your logic down using propositional variables and logical operators. And just an interesting insight that you could have represented this statement using XOR as well. However, you do not have to do that. In this course, like I've mentioned in the previous session, it's only expected that you know the operator or not, the basic operators. When you come into the exam, we expect that you already have knowledge of AND or not. You might have knowledge of XOR, XNOR, or whatever from previous courses, previous knowledge, if we've talked about it in any of the sessions, but we do not right away assume that. So if you do not use XOR, no marks will be deducted. It's just an interesting insight, all right? You can just do the whole thing using OR and NOT. Only these operators, we assume that you know of these things. If we do include a different operator other than the basic ones, we will also define those operators for you in the exam, like I mentioned in the previous sessions. So any questions regarding this puzzle? Okay, so we'll move on to another puzzle. We'll discuss this one again using just our normal natural language. However, I've also given the explanation, laid out the logic as I expect, the minimum that I expect from you based on that. I've also written down the explanation for this puzzle. So go over the explanation in your own free time and understand what is expected of you, how it is expected that you lay down your own logic when you explain the puzzle. The least that is expected of you, I've written that down in the next slide. But before that, let's just discuss this one. Now we have a new scenario, a new puzzle. So here we have two kids, a boy and a girl, who get mud on their foreheads. Let's say they're playing outside and they get mud on their foreheads. They come indoors, their dad sees them, and the dad tells them at least one of you has a muddy forehead. Now, so far, we will assume that all of them, the dad, the boy, the girl, all of them are honest. Okay. Also, they're all capable of making logical deductions. And also that the boy and the girl, they cannot see their own foreheads, but can see the other person's forehead, all right? The boy can see the girl's forehead, but not his own. The girl can see the boy's forehead, but not her own, okay? So these are the things that we know so far. These are the things that we know in this scenario so far. Now, the dad tells them, at least one of you has a muddy forehead. Now, also remember that all three of them are honest. So what the dad says, the statement must be true. At least one of them has a muddy forehead. The dad tells them that, the boy and the girl. Now the boy and the girl know this, that at least one of us has a muddy forehead. Now next the dad asks the question, do you know whether you have a muddy forehead? And to this question, do you know whether you have a muddy forehead? To this question, the boy and the girl can either answer in yes or no. They can either answer yes or no. And also we assume that they answer simultaneously. That is, when the dad asks the question, the boy and the girl, the boy can say either yes or no, the girl can say either yes or no, but they answer at the same time. So the dad asks the question, the boy and the girl says yes or no or whatever, and they answer at the same time. Then the dad asks the same question for the second time. Okay? And the boy and the girl answer again. Now, you are asked to find out what will be their answers the first time and what will be their answers the second time. Okay? So once again, going by the assumptions, what do we know so far? We know that all of them are honest. We know that all of them are capable of making logical deductions. And we know that the boy and the girl cannot see their own foreheads, but can see the forehead of the other person. And they will answer each question, each time they will answer simultaneously. That is at the same time. Okay. Now, let's go with the first time the dad asks the questions. The first time the dad asks the questions, what do you think should be the answer from the boy and the girl? Each of them. What do you think each of them will say? To the question, do you know whether you have a muddy forehead? Please notice that the question is not, do you have a muddy forehead? The question is, do you know whether you have a muddy forehead? All right. To this question, do you know whether you have a muddy forehead? What would be the answer the first time? What do you
No.
think?
No, I guess.
No.
Both of them don't know.
Okay. Fine. You think no. That's fine. If anybody else thinks something else, that's fine too. Because in this course, when we have these discussions here, what's the more important things? The logic behind your answer. So, why do you think that both of them, did you say that both of them will say no, Fardin, Fahim?
Yes, miss, because like they don't know if they have mud on their own heads. They can see the other person's head.
Yes, miss.
Okay. So you're saying that both of them will say no. Yeah, your logic is actually correct, but you missed out some of the steps, all right? So you have to be very pedantic in these cases, all right? Like I've mentioned, you have to lay down every single step. So what you're saying is correct. They will answer no the first time. Both of them will answer no. And why will they answer no? Even that is correct, what you said. That because they cannot see their own forehead, but they can see the other person's forehead. But you missed out some of the steps in the middle. I'm sure that you understand that in your head, but you have to lay it down. Like I've mentioned previously, you have to lay it down. Yeah, go ahead, answer. Expand on that if you want.
The first answer will be no, and the second answer will be yes.
No, we're talking about the first time. Are you talking about the boy and girl? They will give us different answers. Is that what you're saying, Shahriar?
No. The father is asking them twice, right? So
Yeah. The first time, both of them will say no. That's what you're saying.
Yeah. Then second
Yeah.
time, they will say yes.
Yeah, we'll go to the second time a little bit later. We're talking about the first time first. We'll try to deduce first what they say the first time that I asked this question, all right? So what Fardin was saying, that they can see the other person's forehead. They can see that the other person has a muddy forehead. They don't know about themselves, so that's why they said no, right? That is kind of correct, but there's certain steps missing. So we know...
Miss, there's a weather.
Sorry?
There's a weather where you know whether you have a muddy forehead.
Come again?
Means the question is, do you know whether you have a muddy forehead?
Yes. Do you know whether you have a muddy forehead? Yes. To that, they will say no. They do not know whether they have a muddy forehead. But why is that? So, we know that the boy and girl... Yes.
Miss, I changed
Fardin's answer.
Come again?
I want to actually expand on Fardin's answer.
Yes, go ahead, William. Yeah.
The father,
I can say yes also.
at least one of you has a muddy forehead. So, basing on that, they thought that maybe one of them has it. So they look at the other person and they see they have a muddy forehead, and they just assume that they don't have the muddy forehead.
No, they're not assuming anything. See, the question is, do you know? Do you know whether you have a muddy forehead? At that point, since the other person has a muddy forehead, and that is enough to make the statement that the dad made, that is enough to make that statement true, they do not know anymore whether they have a muddy forehead. All right? So yeah, the key point here, the part that you added, I'm sure Fardin understands that as well. He just didn't lay it out. I'm sure that all of you who came to the conclusion that the first time both of them will say no, it was there in your head that the dad's statement is also important here, what you said, William. So yes, we have to combine the two things that we know together. The fact that the boy can see the girl's forehead and the girl can see the boy's forehead, and that the dad said that at least one of you has a muddy forehead, and this statement must be true because the father is honest. All right. So let's talk about the boy. If the boy is capable of making a logical deduction, what must be going on in his head? Okay, I can see that she has a muddy forehead, and dad said at least one of you has a muddy forehead. So the statement, in order for the statement to be true, the conditions are satisfied. At least one, right? So she has a muddy forehead. The condition is satisfied. That makes the statement true. So I no longer know if I have a muddy forehead or not. The question is, do you know whether you have a muddy forehead? The dad is not asking about any assumption or anything. Do you know whether you have a muddy forehead? So I don't know anymore whether I have a muddy forehead, because I can see that she has a muddy forehead, and that combined with the dad's statement makes sense already. So I don't know anymore, because you're looking at least one, right? It doesn't say about at max. Both of them can also have muddy forehead, right? So the boy does not know. What if both of them have muddy forehead? Since the statement, the condition for the statement to be true is already satisfied, because he can see that the girl has a muddy forehead. So now the boy does not know anymore, because at least one, but both can have a muddy forehead, right? So, but the boy does not know. Okay, so he will answer no. Same thing goes with the girl's forehead, with the girl, because the girl is also capable of making logical deduction. We assume that. So same thing goes on with the girls, in the girl's head, and the girl answers no as well, right? So this is something that you have to keep in mind. You have to cover all bases, all right? I'm sure most of you understand this and have this in your head, but you have to cover all bases. However, if you don't, if some part of it is not clear to you, please go ahead and ask question. Please, at any point throughout this course, please do not feel that you cannot ask questions, or do not feel shy regarding asking questions. If you do not want to ask questions here, you can ask me later on, but always make sure that you understand every single thing, every step of the way. Because after this point, we will only build to more complex ideas based on what we know so far. So ask questions, all right? And it's very important to understand it. So far,
Yes,
any questions? Yeah.
Where in the question does it say that the father is honest?
Okay, yeah, good point there. I was hoping you would actually not notice that small loophole there, that it does not actually technically say anywhere that the dad is honest, all right? However, it should have said that, assuming that they can see whether this, yeah, it should have, it says here that both are honest, that the kid, that the boy and the girl are honest, all right? So, however, here, nowhere does it explicitly say that the dad is honest. So the boy and the girl, what if they think that, okay, he's lying? Okay.
So
yeah,
what do we do in this type of scenarios?
you ask me questions. Okay. So
Okay.
yeah, you only know what's given in the scenario. So good point there. I was kind of hoping that I could sneak past it, because it's my problem. It's a mistake that I made. So yeah. So no, you're correct. It's a very good point there. This should have been that all of them are honest, like I mentioned right at the start, assuming all of them are honest. Okay, so good point there. Okay, so assuming that all of them are honest, does everybody understand so far the conclusion that we came to, that the first time the answer will be no?
Yes, ma'am.
Okay, thank you. So now the second time the dad asked the question again. The first time both of them said no. The boy hears the girl's answer, the girl hears the boy's answer. And now the dad asks again, do you know whether you have a muddy forehead? This time, what will be their answer? One of you said that they will answer yes. Was that yes for both of them? I think it was Shahryar.
Means they will get confused and they can say yes. Yes,
It
miss.
should be yes, because
It should be yes.
they heard each other's question as answers, so they know that like both of
Go
them has
go
the-
again, Nafisa. Yeah, I couldn't hear you. So
like
yeah, once again.
they heard each other's answers, right? So
Yes.
they both know that they both have muds on their head, even if they can't see their own heads.
Yeah, you're correct. You're correct. But again, we have to pay attention to the details. Break it down, all right? Break it down to smaller steps and prove it step by step using logic. What you're saying is actually the scenario, but it gives a general idea. I mean, like you have to dig even deeper. That is, break it down. Think of me as a toddler, okay? Think of me as a toddler and think of this as explaining to a toddler, all right? So break it down to every single step in the middle as well. So
If both of them
Yeah.
see the mud on both of their heads and say yes at first, then second time they will also say yes because now they know that both of them have muds on their
So
heads.
wait there. Fadin, you're saying that the first time the dad asks the questions, both of them are going to say yes?
If they say yes, then
No,
the
no,
second time
we're
they
not
will
going
also
with,
say yes.
we're not going with assumption here. This is a different kind of puzzle. Don't get this confused with the other one, all right? So you don't need to assume here. Are they going to say yes? If they say yes the first time, what happens the second time? If they say no the first time, what happens the second time? We're not going with that here. Think of yourself as the boy. Think of yourself as the boy. Based on what you know, if that question was asked to you the first time, what would you say? See, why you don't have to go with assumption here? Because the question is not that do you have a muddy forehead? The question is, do you know whether you have a muddy forehead? Do you simply know or not whether you have a muddy forehead? The answer is not do you have a muddy forehead,
No.
okay?
And
The answer will be
No.
no.
miss, if they cannot
answer
see,
will
then
be
the
no.
answer will be no, miss.
Yes,
Yeah.
exactly.
It will always be no. If they
Um,
cannot see their own forehead.
Not exactly. Not exactly. It won't always be no. This is where I was coming. This is where I was heading to. So this is why, see, Nafisa, this will be clear to you now. This is why it's important to break it down. What you said was correct. But it's not true that it will always be like that. Okay? Why is that? Think about it. So here, it's true that it's the combination of their answers the first time and the dad's statement. Both of them combined, they come to the
May I
conclusion
answer
that,
this?
yeah, sure, go ahead.
The first time, both of them will say no.
Okay.
And the second time, one of them will say yes and the other will say no.
Okay. Why do you think that?
That's because the first time, no one knew that who actually didn't have a muddy forehead.
Yeah.
So the second time, yeah, the second time, the other person will get to realize that actually the other guy who said no, that means he didn't have a muddy forehead. So the guy who'd say yes the second time has to have a
See,
muddy forehead.
the loophole with your answer here is, I'll just point out the loophole. You're saying that the second time one will say yes and the other will say no, right?
Yeah.
See, but they both listen to the answers the first time, right? So both the boy and the girl have the same scenario, same. They know the same things. They have the same scenario. Both of them said no, and both of them heard each other's answer, and both of them were told that at least one has a muddy forehead. They know. Both of them know the same thing, and both of them answer at the same time. So why will one say yes and the other say no? We're saying that both of them has the capability of making logical deductions. So whatever goes on with the boys in the boy's head, the same thing will go on in the girl's head. Because the first time, both answers were no. The first time the answer was no, correct, and I've already explained why that was no. If that is not clear, by the way, the answer why both of them will say no the first time, if that is not clear to you, you must ask a question now, because the second part builds on that. It depends on the first answer. So the first time, both of them will say no. We've talked about this, but I might have missed something or whatever, and it might not be clear to some of you. So if that is the case, then you need to ask now. Is this clear to everybody that the first time the dad asks a question, both the boy and the girl will say no? Does it make sense to everybody?
Yes, miss.
Okay.
Yes, miss.
Yes, ma'am.
Yes.
Yes, ma'am.
Okay, cool. All right. Now let's move on to the second part. Now, think about it. Think of yourself as the boy or think of yourself as the girl and think about it. Now, the first time the question was asked, I know that the other person said no. However, I can see that the other person has mud on their forehead. All right? Because they can see each other's forehead even though they cannot see their own. I can see that the other person has mud on their forehead. But the other person answered no. And also I know that the other person can see my forehead. Okay? The other person can see my forehead. And also, the dad said at least one of you has a muddy forehead. So these are the things that you need to keep in mind. All right? Now I'll build
Miss,
step by step. Yes.
also we have to take in account that the reason that the other person said no is the same reason I said no.
Yes, exactly. Yes, exactly. So now let's build on that. Now, let's think of the boy, for example. So the dad said that at least one has a muddy forehead. And she said she does not know whether she has a muddy forehead. She can see my forehead. All right? She can see my forehead. And the dad said at least one has a muddy forehead. And she answered no, she does not know. Okay? If my forehead was clear, that is, if I did not have a muddy forehead, if I had a clean forehead, then she would have known that, okay, he does not have a muddy forehead, at least one must have a muddy forehead, then it must be me. Do you get what I'm saying? If I did have a clear forehead and she saw that, okay, I don't have any mud on my forehead, and then the dad said that at least one must have a muddy forehead, then she must have, in that case, she would have said yes, because she would have known that, okay, at least one, he does not have a muddy forehead. Then I know that I have a muddy forehead. So I know now that I have a muddy forehead. So I can answer yes. But she answered no. Why did she answer no? It means
Miss,
that I must have a muddy
She can't
forehead.
see that.
Miss,
She can.
is it allowed to answer each of their questions? Like father is asking both of them. Is it allowed allowed to answer, like the boy answers the girls questions and the girl
No.
answers
It's
the boy?
not like that. They will answer their own questions. The father asked them, do you know whether you have a muddy forehead? The boy will say whether he knows whether he has a muddy forehead. He's not going to talk about the girl.
No.
But when he thinks about the logic, see, you're saying that they say yes the second time because since they said no the first time, since the other person said no the first time, it must mean that I have a muddy forehead. Yeah, fine. But you have to break it down to all possible scenarios, all right? So first, think about the case that, okay, she said no, but in what scenario would she have said yes? Think about that.
If the boy did not have a muddy forehead.
Exactly. So you have to think about all scenarios. You have to cover all bases. So both of them will go through the same thought process that, okay, the dad said at least one has a muddy forehead. She can see my forehead. If I did not have any mud, then from that, she would have deduced that, okay, he does not have any mud. At least one has to have a mud. Since he does not have any, it must be me. So I must have a muddy forehead. And from that, she would know that, okay, I know whether I have a muddy forehead or not. I know. So she would have said yes. But since she said no, what does that mean? Since she said no, it must mean that I have a muddy forehead. She can see it. She can see that I can have a muddy forehead. And since she sees that I have a muddy forehead, that's why when the dad says at least one has a muddy forehead, she thinks that, okay, he has a muddy forehead. I don't know anymore whether I have it or not. So that's why she answered no. So you guys, most of you guys explained the no part. Okay, why did they say no? I'm saying that you have to also talk about why if it was not yes. Why it was not yes the first time. That will go on in their head as well. So because this leads to the final conclusion. this leads to the final conclusion. Okay, so she saw that I have a she answered no because she must have seen that I have a muddy forehead, and since I have a muddy forehead, at least one of you has a muddy forehead, that condition is satisfied. So she does not know anymore. That's why she answered no. If I did not have a muddy forehead, in that case, she would have said that she knows, because that would mean that she has a muddy forehead. Since I have a muddy forehead, that's why she answered no. And the same thing goes to the girl's head as well, because both of them answer at the same time, remember? And both of them are capable of making logical deduction. So they will think about both scenarios and finally come to the conclusion that they did not say yes. The other person did not say yes the first time the question was asked. They did not say yes. Why did they not say yes? Why did they not say yes? Because I must have a muddy forehead. If I did not have it, exactly, because both of them have a muddy forehead. We know that. But the boy will think about his own forehead. I can see that she has a muddy forehead, but she does not know that. She does not know that. She can see that what's going on with my forehead. So if she saw that my forehead is clear, she would have answered yes. Because she would have thought that, okay, he doesn't have it, it must be me. But why did she answer no? Why? It must be that I have a muddy forehead, which confused her. She thought that, okay, he has a muddy forehead. The statement that the dad made, it becomes true because he has a muddy forehead. Now I don't know anymore whether I have a muddy forehead or not. That's why she answered yes. Sorry, that's why she answered no the first time. Now, based on the first answer and based on the statement and everything, mainly based on the first answer, now the boy can deduce that, okay, now I know that I have a muddy forehead. Because if I did not have a muddy forehead, then she would have said yes the first time. Since she said no, it means that I have a muddy forehead. That's why she said no the first time. Okay. Now I know that I have a muddy forehead. Now that the boy knows, the second time the question is asked, do you know whether you have a muddy forehead? The boy will say yes. And the girl, going by the same logic, the girl will say yes as well. Okay. So, do you understand, Nafisa?
Yes,
now
ma'am.
that you missed out just on that part, that like, okay, why did they not say yes? You have to also talk about that. All right, cover all
To
steps.
talk about all the possibilities.
Exactly, all possible scenarios. Why did not happen? Think of yourself as the girl, think of yourself as the boy. What would have gone on in your head in this scenario? Okay.
Yes, ma'am.
Ma'am,
Yes.
when the question is asked for the second time, do we have to explain why the answer is not no?
The second time.
Yeah, when the question is asked for the second time.
See, by explaining why it's yes, you're already explaining why it's no. All right. So, the first time, based on the first answer, you have to talk about both scenarios because you have to make a conclusion for the second case as well. We know that for the first question, the answer is no. But we have to talk about why it was not yes. In what case, in what scenario they would have said yes. We have to talk about that to get to the conclusion for the second part. Once you make the conclusion for the second part that both of them said yes, if you back it up with your logic, that is good enough to explain why it was not no. I mean, like it's redundant. The reason we talked about both scenarios on the first, because we still have to make a conclusion for the second one. Once you make the conclusion and once you back it up with logic every step of the way, you're done. Okay. Once you get to the conclusion. So they will say no the first time and yes the second time. I have laid out the explanation here. I will not go over the explanation again. However, if there are questions, I will go over it. Are there any questions regarding the answer? Is there anybody who's confused with the answers? No the first time and yes the second time from both of them for this puzzle?
Miss, can you actually go through this one more time for the last time? Like, why did first time they said no and second time they said yes? Because when you started explaining the second time, I got confused with the first one.
Okay, all right, that's fine. It's very normal. We're having a discussion here. It can always be there, so it's fine. Okay, all right. So the first time when the question is asked, forget about everything first of all. Everything so far, so that you're not confused anymore.
Yes.
Just think about the things that we know in this scenario, the things that the boy and the girl knows. in this scenario. We know that both of them have mud on their foreheads, but we cannot take that into account. We cannot take that into account because the boy and the girl, they do not know for sure that both of them have muddy foreheads. Now, what do they know? They know that the other person has a muddy forehead because they can see the other person, but they cannot see their own forehead. What other thing do they know? Excuse me, sorry. What's the other thing that they know? They know that at least one has
of them has a yes.
exactly. They know at least one has a muddy forehead. Excuse me. So let's talk about the first question. The first time the question is asked. Now, the first time the question is asked, they know that this is true. At least one has a muddy forehead. Now, in order for this to be true, at least one. Remember that it's at least one. It does not say anything about at max or exact one or exactly one. It doesn't say anything like that. It says at least one. It can be both of them. Think about what each of them might think. Think of yourself as a boy maybe. Like, okay, what is the boy thinking? At least one has a muddy forehead, but it can be both as well. But at least one has to have a muddy forehead. Now, when the question is asked, at that point, I can see that she has a muddy forehead. At least one has a muddy forehead. That condition is satisfied because she has a muddy forehead. So at least one does have a muddy forehead. That is true. She has a muddy forehead. I can see it. It makes the statement true. So the condition is satisfied. Now, I don't know whether I have a muddy forehead because it says at least one. Okay. So it can be more than one, right? It can be more than one. It can be both. I don't know that. I can see that this condition is satisfied. I don't know that whether it's both or it's exactly one. Since this condition is satisfied and I cannot see my forehead. So the first time the question is asked, do you know whether you have a muddy forehead? I will answer no. Because I don't know. All right? Does it make sense so far?
Yes, miss.
Okay. So the same thing will go through the girl's head as well. At least one has a muddy forehead. I can see that the boy has a muddy forehead. So at least one does have a muddy forehead. So now I'm confused. What if both of us have a muddy forehead? Because the statement has already been made true. The condition is already satisfied. So I don't know anymore. So no, I don't know whether I have a muddy forehead or not. Now, both of them answer simultaneously. That is at the same time the first time the question is asked. Both of them answer no. Clear so far? Does it make sense to you?
Yes, miss.
Any confusion? No?
No, miss.
Okay. All right. Now, both of them said no and both of them heard each other. So, again, go into the boy's head. The boy, what will be the first thing that will occur in the boy's head? Okay, she said no. She can see my forehead. She can see my forehead. Now, what are the possible scenarios? I know that she has a muddy forehead. The confusion, where was the confusion? In the first time, why did I say no? The first time, why did the boy say no? He can see that the girl has a muddy forehead, but he does not know about himself, whether he has a muddy forehead or not. That's why the boy said no. Now, the second time, since the boy heard the girl's answer, what will he think? Okay, what are the possibilities? I may have a muddy forehead. I may have a muddy forehead, or I may not have a muddy forehead. These are the two possibilities. Now, if I did not have a muddy forehead, then the girl would have seen that my forehead is clear. I do not have a muddy forehead. Then the girl would have thought that at least one has to have a muddy forehead. He does not have it, so it must be me. And from that, the girl must have deduced that she has a muddy forehead, and hence she would have known whether she has a muddy forehead or not. And then she would have answered yes. But she did not answer yes. She answered no. What does it mean? It means that I must have a muddy forehead. Because if I did not have a muddy forehead, by seeing that I have a clear forehead and also by listening that at least one has a muddy forehead, the girl would have thought what? Okay, he does not have a muddy forehead. At least one has to have. So among the two of us, if he does not have it, it must be me. And then from that, she could have deduced that, okay, I know that I have a muddy forehead. So the answer is yes. She would have said that if I had a muddy forehead. But she answered no. What must that mean? It must mean that I have a muddy forehead. So from there onwards as well, you have to lay down the logic, by the way. Yeah. So it must mean that I have a muddy forehead. The girl sees that I have a muddy forehead, and since she can see that I have a muddy forehead, and she can combine that with the statement at least one has a muddy forehead, and since I have a muddy forehead, at least one has a muddy forehead, that statement is true, and that's why she doesn't know anymore that she has a muddy forehead or not. That's why she answered no. All right, see, only if I had a muddy forehead, only then she would have been able to answer that. Only if I did not have a muddy forehead, only if my forehead was clear, only if I did not have a muddy forehead, she would have known whether she has it or not. And the same goes on through the girl's head as well. Only if I do not have a muddy forehead, he would have known whether he has it or not. Since he does not know, and since she does not know the first time, since they do not know, it must mean that I have a muddy forehead. She can see it. That's why adding that with at least one has a muddy forehead, by combining those two conclusions together, she gets to the point where she does not know anymore whether she has a muddy forehead or not. That's for the first part. All right. And from there, you can deduce that, okay, it must mean that I have a muddy forehead. The reason I explained this so much, this further, and the reason this might get confusing for you guys, even though it gets confusing for you guys, I went this far because this is something that you are expected to do as well. All right. So the first time both answered no, to that bit you are clear, fine. But after listening to each other's answer, what are the possibilities for each of them? The boy, think about the boy. The boy knows that the girl has a muddy forehead. He does not know about his own. So what are the possibilities? The possibility is that I have a muddy forehead or I do not have a muddy forehead. If I do not have a muddy forehead, then what would have been her answer to the first question? If I do not have a muddy forehead, her answer to the first question would have been yes. But it was not yes. It was no. Then it must mean that I have a muddy forehead and yeah. Okay. And in between as well, the logic, like I've mentioned already, you have to lay it down. You have to explain the whole thing, every single part. Okay. Is it clearer now, or is it still confusing, or even more confusing?
No, it's clear, but there's a high chance I'm going to mess it up again soon.
So for that reason, I have laid out the explanation here, and of course the recording will be available as well. You can go over that, and it's confusing. Of course, like I've mentioned many times, send me an email, ask for consultation, ask me a question again in the next session. Whatever you do, it's fine. All right. So the key thing is here to understand clearly, because obviously you're not going to get these exact puzzles in the question. All right. In the question, you will get a new puzzle or a twisted version of this, anything. All right. You should expect something new in the question. So the important thing here is for you to be able to make a logical deduction. And when I say that, I am not obsessed with the answer. I am obsessed with how you got to the answer. You have to lay it down with logic, and every single step must be mentioned. All right.
Miss, I have a question.
Yeah.
Miss, was the actual scenario here? Both of them has a muddy forehead, right?
Yeah. We know that, but they don't know that. So we have to think from their perspective. What would be their answers, knowing the things that they know. Okay.
Yes, miss.
All right. Any other questions? Any remaining questions?
No, miss.
Okay. All right then. So if everybody's clear with this, then I'll move on to the next topic. Go over this explanation in your own free time so that it's clear to you, and make sure that you are able to lay down the logic for future puzzles in this manner, at the very least in this manner. Okay. Now, tautology. What is a tautology? We've already actually talked about a tautology. What is a tautology? A tautology is a compound proposition, a compound proposition that will always be true, regardless of the truth values of the propositional variables that are there in the compound proposition. Okay. So compound proposition, notice that here. It's not very important, but an interesting thing that I wanted to mention related to what we said previously how we defined a proposition. If a proposition is not a compound, then what does it mean? It means that the proposition has only one variable and no logical operators are there. All right. A compound proposition is combined with multiple variables and connected using a logical operator. If for a simple proposition, all right, for a nuclear proposition, for example, if you must a nuclear proposition, if you can say it that way, there are no operators there, right? If there are no operators, the proposition in its normal form can either have a true value or a false value. Okay, that is how we define a proposition. What is a proposition? A statement that can either have a true value or a false value. However, a tautology will always have the truth value of true. So that's why we define tautology in terms of compound proposition. Because if a proposition on its own, that is no combined with no other proposition, with no logical operators, nothing like that, just a single statement, a single proposition, a singular simple proposition, if that is a tautology, then that is not a proposition anymore, because a proposition can either have the truth value of true or false. For example, I used the example that the sun rises in the east, whether this is true or false. We know that it has a definite truth value based on our knowledge of the physical world, or the world outside of this these lectures. But when we come to these lectures, when we get here, we don't know anything from there. All right. Once again, a reminder for you guys, because this is where many people get confused. Okay, this is common sense. All right, this makes sense. I don't have to talk about it, or I can just assume this to be true because this makes sense. No, you cannot. You only go with what you know in the given scenario. In the question, if it says that a certain proposition is true, or the certain value of a certain proposition variable is true, then you go by that. If it's false, if you go by that, you go by that. If it's not said, it can be either true or false. So whatever is said in the scenario, you go by that. You don't assume anything. Okay. So a tautology is a compound proposition that will always have the truth value of true, regardless of the truth values of the variables inside it. What is an example? An example is this: P or not P. This is a compound proposition because you have an OR operator here combining two propositional statements. Now, P or not P, this is a tautology. Why is that? Does anybody have any insight? Why are we saying that P or not P is a tautology?
Because it has to be P or not P.
It has to be P or
Always.
It has to be true. At least one has to be true, right?
Yeah.
At least one will be true.
Always.
At least one will always be true. If P is true, that makes the whole thing true because it's an OR operator. All right. If
Yes,
P, even if P is false, if P is false, what happens to not P?
Not P is true.
Exactly. And since it's the OR operator, it makes it true. Okay. In terms of natural language, if we represent the variable P with the statement, if we represent the variable P with the proposition, it is raining. P represents the proposition, it is raining, which can be true or not true. If this is not true, then what does it represent? It represents the proposition represented by not P. Not P is what? It is not raining. So you see here, even in natural language, it makes sense. It is raining or it is not raining. At least one must be true. If it is raining, then you have it true. If it is not raining, then this is true, and that makes it true. So this will always be a tautology regardless of the truth value of P or not P individually. Okay? Does it make sense to everybody that P or not P is a tautology?
Yes, ma'am.
Okay, let's move on to a contradiction. What is a contradiction? A contradiction is opposite to the idea of a tautology. That is, a contradiction is a compound proposition which will always be false, regardless of the truth value or the propositional variables that are there in the compound proposition. A contradiction is a compound proposition that will always be false. An example is P and not P. Here we have the logical operator AND. In case of an AND, remember, how did we define an AND? If you have the AND operator, the result will be true only and only when all of the variables are true. That is, in other words, this will be false as long as at least one of them is false, right? So now, let's assume that P is true. P can either be true or false, right? P is a propositional variable representing a certain proposition, right? So it can either be true or false. Let's assume first, let's go by the case that P is true. If P is true, guys, since this is an AND operator, if P is true, is that enough to make the statement true?
No.
No. We have to look at not P as well. However, if P is true, what happens to not P?
False.
False. Exactly. And since this is the AND operator, if this is false, the whole statement becomes what?
False.
False. Exactly. Let's look at the other scenario. What if P is false? In that case, guys, do we even need to look at not P if P is false? Do we even need to consider the truth value of the other one if P is false?
No, miss.
No.
No.
Because this is the AND operator. If even at least one of them, if at least one of them is false, it makes the entire statement false. So you see, P can either be true or false. But in both cases, in both scenarios, P and not P will always be false. Because if one is true, the other one will be false, always. So this will always be false. So this is an example of a contradiction. A compound proposition which will always be false. It is raining and it is not raining. Both cannot be true at the same time. One will always be false, and which will make the whole statement false. It is raining and it is not raining is a contradiction. You cannot have both to be true at the same time. It doesn't work. It's a contradiction there. Everybody understands contradiction and tautology? Okay, then we can
ম্যাম
move on.
আরেকবার এক্সপ্লেন করেন, আমার নেট চলে গেছিল।
All right, no worries, it's fine. So contradiction, the way we define a contradiction, it's just the opposite of a tautology. Did you understand what a tautology was?
Yes, ma'am. Either that's true or not, something like that.
No. A tautology is a compound proposition, is a compound proposition which will always have the truth value of true. A compound proposition will always have the truth value of true, regardless or irrespective of the truth values of the variables in the compound proposition. For example, P or not P. Regardless of what the truth value of P is or not P is, regardless of that, whatever it is, a proposition can either have the truth value of true or false, right? So whatever the truth value of P is, regardless of that, this compound proposition will always be true. Okay? So how is that? How does that happen? Because think about it. This P, this propositional variable P, if it's a proposition, it can either be true or false, right? So if it's true, we'll go by case by case. Once when P is true and the other one when P is false. If P is true, since this is an OR operator, and in case of an OR operator, as long as at least one is true, it makes the entire statement true. So if P is true, it makes the whole thing true. That's one case. What is the other scenario? The other scenario is P is false. If P is false, we can still look at the other part of the statement because it's an OR operator. We can look at not P. If P is false, even if P is false, not P becomes what? If P is false, what happens to not P? True, exactly. Not P becomes true. And since this is an OR operator, as long as at least one is true, the whole thing is true. So you see, at least one of them will always be true. If P is true, then that makes the statement true. Even if P is false, not P becomes true, and that makes the statement true. So you see,
Yes,
whether P is true or P is false, whatever be the case, it does not matter, irrespective of the truth values of the variables in it. It does not matter what the truth value of P is. This will always be true, P or not P. So this is a compound proposition which will always be true. So this is a tautology. So contradiction is the opposite, a compound proposition which will always be false. An example is this, P and not P. So you see here we have the AND operator. And you remember, for an AND operator, if
I need two yes or something, two truths.
in case of an AND operator, you need the result of an AND operation The result of an AND operation will be true if and only if all of the variables are true, right? Or in other words, the result of an AND operation will be false as long as at least one is false. Like the AND operation, in an AND operation, if at least one of the propositions or one of the variables is false, it makes the entire statement false. All right, remember that? Now, in this AND operation, see, again we have P. P is a propositional variable. It might have the truth value of true or false, whichever. But we are saying that it does not matter. Ultimately, the result of this entire statement will always be false, regardless of the truth value of P. Now, if P is true, let's go case by case. If P is true, you tell me, is it enough to find out the truth value of the AND operation? If P is true, will that make the entire thing true? Will that make the statement true? If P is true.
Basically, we need two truths for the AND value to be correct.
Sorry, come again?
We need two truth values to. We need two truths to make the AND value true.
Yes, exactly. Very good. So if we consider the scenario when P is true, that is not enough. We also have to look at not P, right? So what happens to not P if P is true?
It becomes false.
Exactly. You just said that we need two truths here. This one is false, so this makes the entire statement what? False. Okay, let's talk about the other possible scenario when P is false. If P is false, do we even have to look at not P? No. If P is false, since this is an AND operation, if even one of them is false, then that makes the entire statement false, right? So since P is false, it makes this entire statement false. Okay, so P and not P, as you see, regardless of the truth value of P, whatever the truth value of P is, and correspondingly whatever the truth value of not P is, the result of P and not P will always be false, and that is a contradiction. That is an example of a compound proposition, which is a contradiction, always having a truth value of false. Okay, now I want to talk about equivalence in case of compound propositions. Two compound propositions are said to be logically equivalent if both propositions have the same truth values for all possible combinations of the truth values of the variables in it. All right, and the symbol we use for logical equivalency is this one, 3 bars, like this one. So two compound propositions are equivalent when they have the same truth values for all the combinations in the truth table. Let's look at an example. So we have two compound propositions here, this one on the left hand side and this one on the right hand side. So we need to check, or we need to show that these two are logically equivalent to each other. How do we do that? Using a truth table. Using a truth table, the way to do that is for all possible combinations, you have to find out the truth value of the statement on the left hand side. You have to find out the truth value of the statement on the right hand side. If both these statements have the same truth values, we're not saying whether it's going to be false or true or whatever, but if it's false, false for both of them. If it's true, true for both of them. If they have the same truth values for all possible combinations, then they're logically equivalent to each other. All right, so now let's see how we can do that using a truth table. Let's look at the first combination. First combination for both statements. The first combination, before that, can anybody tell me why do we have 4 combinations here?
This is because there are 2 variables.
Yes,
On top of
exactly.
each
2
other.
variables, so 2 squared, right? 2 to the power
Yes,
of 2, so 4 combinations. So the first combination is true, true. That is the scenario where P is true and Q is true, both of them. So here, what we will do? We will apply these truth values, this first scenario, the first combination, true, true, we will apply that in these statements individually. Let's go with the left one first. Okay, so here, we will apply true, true for P or Q. We will do true or true. So P is true, Q is true, then true or true will give us what, guys?
True. True.
True. Okay. And then what will we do? Apply the negation on that. Negation on true. The result of P or Q is true. The negation on that will give us what?
False.
False. So we have false here. Now, why did I do P or Q first?
Because the bracket rule
Inside
has
the
to
parent.
go to
Yes,
precedence.
exactly. the parenthesis always comes first. What if I didn't have a parenthesis? What if the left statement did not have these parentheses?
Then it should be not P or Q.
That is, you apply the negation first.
Yeah.
On which one?
P.
P, exactly, correct. So if you didn't have the parenthesis, it would be not P first. That is negation on P first, and then you apply the OR operation, all right, based on the precedence. Okay. However, we do have parentheses here. That's why we did P or Q first, and then on that we applied the negation. So we have false here. Now let's look at the statement on the right-hand side. We have true, true here. So apply the truth value of true here for not P. We have true for P. What happens to not P, guys?
False.
False.
False. Okay. And then what do we have? The negation on Q. What is the truth value of true? Sorry, TQ, true. So not Q becomes false. So false and false gives us false. Okay. So again here, why did we do the negations first?
This precedence.
Exactly. So based on precedence, negation comes first. So you have to apply the negation on P individually. Individually, you have to apply the negation on P first, and you have to apply the negation on Q individually. Again, individually on Q first. Then once you apply the negation, you get false here, and then you apply the AND operation. False and false gives you false. Okay. In fact, you don't have to do this, what I'm about to tell you, but if you want to fast track, then just if you understand the definition of AND, actually, the moment you get a false here, you can say that the result is going to be false, right, guys? Because in case of an AND operation, we know that even if at least one is false, that makes the entire statement false, right? So the moment you get false here, you wouldn't even have to look here. False and false, right? Okay. So here as well, inside we have an OR, right? The moment you see that P is true, and this is an OR operator, and in case of OR, what do we know? In case of OR, as long as at least one is true, that makes the entire statement true. So if P is true, the moment you see P is true, you don't even have to look at Q. So yeah. So I just mentioned that for so that if you ever want to apply these ideas and do things faster for that, but you don't have to do this. In fact, at the start, I would recommend doing everything case by case, following the precedence, all right? That is, do P or Q first, then apply negation. Otherwise, many of you might get confused or make errors, all right? Apply the on the right-hand side, apply the negation first and then AND, all right? And through more practice, you will see that these things will come naturally to you. You will do these things a lot faster, all right? So for the second scenario, again, do the same thing. On the left-hand side, you have true for P and false for Q. And true or false gives us what? True or false gives us what, guys? True or false?
It's true.
True.
Yes. And negation on that gives us false. So
False.
we have false here. Here, again, apply true and false. For P, we have true. So not P becomes what? False.
False.
Apply false in Q. So not false becomes what? True. So we have false here and true here. However, this one is an AND. So false and true. Because of the AND, false and true gives us what?
False.
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 So there you go, false here. Similarly, you apply the other two combinations as well in each of these statements and then come up with the result, and you will see that they have the same values. And since they have the same values, we can say that these two are equivalent to each other. Now, instead of doing this mental math sort of, instead of that is doing all of this in your head, what you can do also is add more columns in the truth table, okay? That is, let's say for the statement on the left-hand side. What do we do first? We do the OR operation first. You can add a column here dedicated to P or Q, just P or Q. Add a column here for P or Q. So based on these values, you will find the truth value for P or Q. And then this column where you apply the negation on the truth value from the previous column. Just reverse the truth values, all right? So one column you will have P or Q, and then not P or Q will give you just the reverse value. Same goes for the next one. Okay, the statement on the right-hand side. You could have a dedicated column. You could add a column for not P and then add another column just for not Q and then perform the AND operation for those two columns. Okay, you could have done that. Why? Just to make things more clear, just to make things clearer for you, just to make things easier for you at the start so that you don't ever make mistakes. Okay, so when you start off, when you start practicing, I would say go with this. Create columns for each of the operations individually, and then find out the ultimate truth value for the final statements. All right, I would recommend doing it like that. That is breaking up the entire task, so that you do not make mistakes. And then through more practice, you will see that you can do the whole thing in your head. Okay, but initially you could do something like that. Break the operations down based on precedence, and then create columns dedicated to each operation, just like this one here. So here we are asked to show that these two statements are equivalent to each other. Here in both these statements, you'll see that we have 3 variables. So that should tell you that you can have more than 2 variables. You can have, in fact, more than 3 variables. You can have any number of variables in these statements. All right. So we have 3 variables here. So we will have to the power of 3, 8 combinations, 8 possible combinations here. And as you can see here, we have 2 columns here for P or Q, P or R. Why? Why do we have that? Just to show you that you could have broken this entire process down. That is, if you look at the statement on the right-hand side, represented by B here. B represents the statement on the right-hand side. The right-hand side, which operation will happen first, guys? For the right-hand side, which one will we do first?
The OR operators.
Exactly. We will do OR operation first. We will do P or Q first, P or R first individually. So that's why we have dedicated columns for P or Q, dedicated column for P or R. Once we compute the truth value for P or Q, the truth value for P or R, then what do? We do the AND operation between these 2 values. So if you do P or Q, which is easy, very easy, if you do P or R, just by looking at these 2, you can do P or Q, P or R. It's very easy, right? You know the truth table for OR operation. Once you do that, then you apply AND on these truth values. All right. Now to find out B, find out the truth value of B, what do you have to do? True and true, true, true and true, true, and so on until here, and then true and false, false, false and true, false, false and false, false. So you could have done something like that. All right, just to make things clearer, so that you don't make any mistakes at all. Same goes for the statement on the left-hand side. You could have you could have had a dedicated column. You could have added a column for Q and R, another column where you compute Q and R. So based on the truth values in each of the combinations for QR, you compute the truth value of Q and R in that column, and then you apply the OR operation between this column, between the P column and the Q and R column, and then come up with the result for A. You could have done something like that to avoid confusion. Okay, so the same process that I explained here, same process goes here. For each and every combination, you take these truth values. For example, for the first one, true, 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 apply them here, and then see what the result is. So I would recommend trying this out without looking at the truth table. Try this out on your own and see if it matches. Okay. Some obvious equivalences that you should have surmised by now. P or P will always give you P. All right. So obviously, it's the OR operator, and it's the same variable on both sides. So P or P will equate to P. P and P also equates to P. P or Q is equivalent to Q or P. That is, as long as you have the same operator throughout the statement. Throughout the compound proposition, if you have the same operator, you can change the position in whichever way you like, and the result would still be the same. See, we have only OR here, only one single operator, the same operator here. So P or Q, if you change the position, it's the same thing. Same goes for AND. As long as the same operator throughout the entire proposition, even if you change the position of the variables, it will give you the same thing. P and Q is equivalent to Q and P. This is something we call the double negation law. Something like minus minus is plus. All right. So negation applied on negation of P will give you P in its normal form. Right. So these are some of the obvious equivalences that you need to know about for some of the things that we will discuss later on. All right. And these are some other equivalences that you also need to know about, some other important equivalences. All right. So P implies Q is equivalent to not P or Q. This is something you need to know about. Also, this can be derived. Okay. All of these equivalences, you can actually derive them yourselves. not P imply P implies Q. P implies Q is equivalent to not P or Q. This is actually derived from something that we've already done. Remember the truth table for the implication? Okay, here P implies Q. We expanded it in this format using these ands and nots and ors. This can be actually, these expressions can be combined and brought down to a more concise version or a smaller version. And from this on the right hand side, you can actually apply the other laws and convert it to a smaller version. Okay, this actually comes from that one. That expression actually is derived into this expression or converted to this smaller form. How? By applying other laws like the distributive law. For example, the distributive law, what does it say? It is very similar to your idea of P multiplied with Q plus R. If you had a variable P and a variable Q and an R in your normal mathematics so far that you've seen, each representing numbers or whatever, if you had P multiplied with Q plus R, how would you do that? PQ plus PR, right? That's how you distribute it, PQ plus PR. So the distributive law of mathematics is the same thing here. So here, the operator that you have inside and the operator that you have outside, that's important, all right? So see, what we do is, the operator we have on the outside here, OR is on the outside. What do? We distribute this OR to each of the variables in the parentheses. You distribute the operator outside. Here we have OR outside. So you distribute this OR to each of the variables, all right? So P or Q, P or R. And then this AND operator that was there in the parentheses, this AND operator that was there between the Q and R, you put that here in between. Same goes for the other scenario where you have AND on the outside and OR in the inside. You distribute it the same way. You distribute this AND operator to each of these variables in the parentheses. So P and Q, P and R. And this OR comes in between. So distributive law. And remember that each of these are equivalences, so they go both ways. You can go to the right one from the left one, or you can go to the left one from the right one. From the earlier example or the earlier derivation of P implies Q that we did in the previous session, from that one, you could get to this one by applying the distributive law. That is, you have this on the right-hand side. And on the left-hand side, you have the more compact version or the smaller version based on the distributive law. So you can apply the distributive law there and combine this to get here. Okay. You would also actually have to use the associative law there. What is the associative law? In the associative law, it says that as long as throughout the compound proposition, again, as long as throughout the compound proposition, all the variables are the same, as long as that's true, you can change the position of the variables. You see, here you have only ORs, P or Q and OR outside as well. As long as the key thing is here, the key thing here is that the variables are the operators are the same. As long as it's the same operator throughout the compound proposition, you can change the positions, switch the positions of the variables, and it would still be the same thing, all right? Same goes for OR and AND. Even in case of the AND one, as long as it's the same operator, as long as you have only AND throughout the proposition, you could switch the variable position and still end up with the same thing. That's the associative law. However, if you have a combination of different operators, in that case, you would have to go to the distributive law. This is something that we already know as well. An implication is equivalent to its contrapositive. The De Morgan's law also makes sense. So you have P or Q inside the parentheses. What would you do? You would have to apply the negation individually on each of these variables. So you have the negation outside, right? So you apply the negation on each of these variables individually. Not the negation, the not operation is applied on P individually and then Q individually, and the operator in the middle, the operator inside the parentheses. The operator inside the parentheses. How do we apply the negation on this one? By applying the negation on the OR operator, it is just inverted to the opposite one, which is the AND. Same goes for AND. If you have this scenario, first, again, you apply the negation on each of the variables first. So negation on P, negation on Q, and the operator inside between these two variables, the operator is just inverted. The opposite of the operator, you have that there. And these two are equivalent. You can convert this expression on the right hand side to the left one or the left one to the right one. So that's the De Morgan's law. So these are the equivalences that you need to know of as well. You can obviously derive them. You can obviously just understand them and remember and derive them in the exam and go to it from that in that way. However, I would recommend that practice so much, practice more and more equivalences and these things so much that you always remember these laws. Why is that? Because in the exam, I can guarantee that you won't have the time to derive from the more expanded version to this compact version by applying these laws. You won't have the time to get to this one from this one in the exam when you need to apply these laws or these equivalences, all right? In the exam, you need to remember that, okay, P implies Q is equivalent to not P or Q. You need to remember that to make things faster, all right? So practice so much that you always remember these things, okay? Even before deriving, or even if you derive, you don't have to spend too much time. Okay, this was this, okay, fine. So that it's faster. You won't have enough time in the exam to derive these things. So if you remember these equivalences, then it'll be easier for you to apply this in the topics that will come later on in the next session. These are some of the, again, obvious equivalences involving tautologies. We have discussed some of this actually when we're talking about other concepts. For example, when you have an OR operation, if at least one is true, then that makes the entire statement true. So P or true, regardless of the value of P, no matter what the value of P is, if you have an OR operator and this one is true, P or true will be true, whatever the value of P is. In case of an AND operation, however, both has to be true in order for them to be true. And if at least one is false, the whole thing becomes false. So in case of an AND operation, if one side is true for sure, then the result actually depends on the truth value of P. So P and true is equivalent to P. P or false. In that case, the truth value depends on the value of P. P and false. Since it's the AND operator, since we have one false here, it makes the whole statement false. So regardless of the truth value of P, this becomes false. And P or not P is true, and P and not P is always false. We've already established that in tautologies and contradictions. So go over these slides, go over these obvious equivalences and these important equivalences and understand these, and then we will pick up from this slide in the next class. All right? So, any questions so far?